All right, integral properties. I think this is the name that most books use. Some teachers really gloss over this, but if you're in an AP class, it'll definitely be emphasized, or at least glossed over enough that you should maybe remember it for a multiple choice question somewhere on the AP test. So we'll just go over it real quick. Basically, this is just a question when you're dealing with definite integrals from like -1 to 2 or whatever. This just deals with, well, hey, what if we switch an integral from -1 to 2 to being from 2 to -1? Ooh, what's going to happen, you know? Pretty lame, right? Other things, like in the previous video about the areas and definite integrals, we took an integral like from -1 to 2 and we broke it into an integral from like -1 to 0 and then added that to an integral from 0 to 2. So overall, it ended up going from -1 to 2. That's another integral property. So we can also multiply stuff and whatever. You'll see. We're just going to go through them real quick. It's a very basic type of problem, and most students don't seem to have too much trouble with it. All right, so switching up our lower bound. All we're doing, if you were integrating from a to b, and then you switch it to be for b to a, all you're doing is getting the negative answer. But that actually makes perfect sense, right? Because when you've plugged in a and b, you got like some function of a. Sorry, we put b. We did the upper bound first, so when you evaluated this at the end of the problem, you got f of b minus f of a. Well, guess what? If you put a negative sign out front, well, if you put a above b, then it's going to be f of a minus f of b, because you do the top one first, then the bottom one. So if you put another negative sign out front, though, like right here, that just switches the order back to being b minus a. So that one's kind of self-evident, and we'll do a practice problem with these in a second. Breaking up integrals, like I said a second ago, if we were integrating from a to b, so say that's a and that's b, so the integral from a to b would just be all of this area. Well, guess what? If you throw a random number in c, like right here, we're just saying, you know what? The area between a and b, so that whole area, is the same as the integral from a to c, plus the area from c to b. It's kind of self-evident, speaks for itself. If you break up one bigger piece into two halves, obviously the halves add up to the whole. So that's not super surprising. All right, so let's just take a crack at a couple of examples with actual numbers. So this is the way they tend to give you these questions. They won't tell you the function itself. They won't give you x squared minus 6x and that kind of junk. They'll just tell you, hey, the integral from 0 to 2 is 6, and the integral from 2 to 5 of that same function is 3. And then they'll ask you for an integral that has different limits of integration than either of the things above. So if we want to know the integral from 0 to 5, what we should do is realize, well, hey, wait a minute. If I look at these numbers up here, I don't have from 0 to 5, but I do have from 0 to 2 and 2 to 5. So really, there's just that property we talked about where you can take a whole and break it up in two halves, or if they give you the two halves, you could combine them into a whole. Because the integral from 0 to 5 is really just the same as the integral from 0 to 2 plus the integral from 2 to 5, right? And of course, from 0 to 2 they just told me is 6, and from 2 to 5 they just told me is 3. So that ends up being 9. That's how simple these are. And we can also, we've done this a lot already when we've integrated stuff, and the derivative also. Whenever you have a constant, like this 3 here, you can just move it out front. So even though we don't know the integral of 3f to the x, that's really just going to be the same as 3 times the integral from 2 to 5 of just plain old f of x. And of course, the integral from 2 to 5 of plain old f of x is what I got right here. It's just 3. So this is 3 times 3, which equals 9 again. Not too bad, right? They call these integral properties, but really it's just kind of like you had log properties in algebra, in a precalculus, where the natural log of one number times another number was the log of one number plus the log of the other number. It's just those rules that allow you to combine and break up things. That's all this is talking about. All right, if you want to, let's see. So here we have something interesting. I was just looking at 0 to 2 and 0 to 2 and I got confused, but look at this. We got a different letter, f of x and g of x. All right, let's see what happens. Let's see, well, they want to know the integral from 0 to 2 of f plus g. Oh my goodness. They didn't give us that function, but there's this other integral rule, and we've kind of been doing this all along with polynomials. If you have the integral of something plus something else, that's really the same as the integral from 0 to 2 of f plus the integral from 0 to 2 of g. We can essentially sort of distribute in this integral sign to the f and the g separately. Since they're added together, same would be true if they're subtracted. You can't do that with multiplication or division, but when two things are added or subtracted, you can do that, separate it into two separate problems. And of course, we already know what the integral from 0 to 2 of f is. It's 5. And we know what the integral from 0 to 2 of g is. It's -2. So that's just going to add up to 3. So you can see how contrived this was. They gave you two very specific integrals, and then just gave you, kind of had to, combine them in the right way. Let's try doing the same thing. So always some slightly different numbers. Now I've got a constant in there, plus we got to split it up. So this is going to be the same as 0 to 2, 3, if we move that 3 out in front of the integral. So that's 3 times the integral of f minus the integral from 0 to 2 of g. Alright, so that's 3 times the integral of f. So that's 3 times the integral of f from 0 to 2 is 5 minus the integral of g, which is -2. Of course, those cancel, so we get 15 plus 2 is 17. Not too bad, right? Once you it seems like when I've tutored students in this particular area, it seems like it kind of looks like Greek, like you have no idea what to make of it. But then once you see how to do the problems, you're like, oh, that's all they meant? It's kind of like, kind of cheese ball. All right, breaking up integrals. Let's see what happens here. All right, so this time we've been given the integral from 0 to 7 and the integral from 3 to 7, and they're asking for the interval from 0 to 3. So whatever this function looks like, we don't know. But basically, if here was the graph, they've given us the integral from 0 to 7, which is from here all the way up to 7. And they've also given us the integral from just 3 to 7, so they gave us this. And then they're asking for just this portion. So this one's a tiny bit trickier, but basically, isn't this portion we want just going to be the big one minus this right half? I think so. So that's just going to be the integral, the larger integral, which is from 0 to 7. And then we got to subtract the integral from 3 to 7, which is this smaller portion on the right. And this should give us the portion on the left, which is what we want. So integral from 0 to 7 is 6. And we got to subtract 3. So that's going to equal 3. Now just a little note on notation. If you look at how I just drew this, I didn't put f, I didn't put dx, I didn't put f of x in parentheses, just because I wanted to make this more obvious what I was doing. If you have a rigorous teacher who's really mean and likes to take away points, you might need to write this as 0 to 7 of f of x, and also use a snooty British accent, kind of upper crust accent while you're doing it. So you're like, integral of f of x dx minus the integral from 3 to 7 of f of x dx. But if most teachers, as long as they see roughly what you're doing and you get to the right answer, and this to me, was like as much work as you'd have to show. Granted, I'm not an AP teacher, but it seems like teachers are usually pretty lenient on this type of work because, either you know how to do this or you don't, but there's not a lot of work to show anyway. So there you go. That's integral properties. Point is we can subtract these, we can add them, we can break areas up or put them together, you name it. That's what this whole chapter is kind of all about.